Thanks for coming to our session. My name is Jakub Zavrel, founder of Zeta Alpha, and I'm going to do this talk with Arthur here, who's a research engineer at AI research engineer at Zeta Alpha. And we're going to be talking about how to develop these kind of more advanced orchestrations, more advanced AI agents like deep research that have a lot of value for business users, how to develop that on private data, and in particular, when you develop these kind of more advanced agents, you run into the problems of evaluation on domain-specific contexts. And then Arthur is going to do the second piece of the talk, where we're going to talk about how to use evaluation to actually drive kind of self-learning and self-optimization using advanced agent optimization techniques. So for those of you who don't know us, we're Zeta Alpha. We're a local shop founded here in Amsterdam, but with global ambitions. And we help large companies, especially in the chemistry and industrial manufacturing space, where standard AI models need a lot of customization before they become accurate, to move faster from prototype to production in use cases like advanced retrieval augmented generation, AI agents, and in general connecting generative AI to internal knowledge and expertise in these companies. So at the heart of that is retrieval augmented generation. So basically the ability to let a large language model answer a question accurately with grounding in the internal documents, the internal knowledge bases of a company. And that might come in the form of a kind of enterprise search type of interface, or it might actually be in some kind of securely deployed private chat, GPT-like interface, which more and more, which you see in these buttons here at the bottom, is becoming a kind of platform to deploy task-specific and role-specific agents that perform automations for a particular task. And one of the interesting ones, of course, is deep research, which especially in like R&D context or engineering context, gives a much more useful type of RAG answers than just simple RAG. And I won't go now into the full sort of specifics of our platform, but we're basically automating the whole workflow from capturing data from many different enterprise applications, deploying that securely on in the private IT infrastructure of companies, and then customizing both the search behavior to the specific knowledge and expertise, and also the agent orchestration to that. And so they kind of started as RAG, and this is a very simple sort of RAG diagram, which I think many of us today understand that just having a vector database and injecting document chunks into the context of the LLM prompt is not entirely like how you build production systems. So in fact, of course, search accuracy is super important. So the actual search looks a lot more like kind of hybrid mesh of different search strategies, lexical BM25 search, vector search, fine-tuning the models, putting re-rankers on top, and then putting a lot of LLM tools actually to both pre-process the query and to interpret the search results to come with accurate answers. So in fact, sort of the state-of-the-art modern industry RAG pipeline looks a little bit more like this, where you have a lot of LLM-based pre-processing of the query, then you have multiple search strategies, you fuse them, you re-rank, and then you build your answers. So this pattern is kind of evolving further into more complex agentic systems, where you have these different modules, and you actually have a top-level agent, often called an orchestrator, which actually starts with the user query, creates a plan how to invoke all these different subcomponents or modules, and these modules then interact in various ways, divide the tasks evaluate each other, write intermediate results into memory, and synthesize that ultimately into a sort of task completion for the user. And one of the interesting applications of that is deep research. So obviously, if you have a rack system and you're a chemical research scientist, and you have this question here, innovative structural changes to these bioplastics, and you get from top 5, top 10 search results, this generated answer is correct. It's actually grounded in documents. But for a research scientist, this is not very useful because they probably already know all of this. They're really looking for a much more complete answer, which is not missing anything that has been done previously in the company and is going to provide a lot higher level of detail. So what we do, and Arthur will talk about the more specifics of that, is actually subdivide this task into like planning out from the initial user query a bunch of different search aspects and executing those searches, and then using LLM as a judge evaluation to actually figure out which documents are relevant for this query, if they maybe uncover some new aspects of the problem or the solution space, generate an answer, and then critique that and iterate multiple times until it converges to a more complete answer. And this actually, for the research scientist, yields a much more useful result, not just a short answer with some grounding in documents, but actually like a multi-page, fully complete overview of the whole research area that normally they would take like hours or days to compile. So this is very useful. Our users are really appreciating that. But the question now comes, if you're like a chemical research scientist in a particular area, how do you evaluate that? So our knowledge engineers and consultants, they cannot actually understand whether a particular report is fully correct and adequate for the research scientist in a specific niche. And the research scientists don't really want to spend their time on annotating search results or have the capability to even generate proper feedback or have data to evaluate these systems on. So the first part of evaluation is really about generating data. And we have pioneered a method called InParse, which basically generates synthetic data from the search index to fine-tune these models. And of course, if you have synthetic data to fine-tune these search models with questions and documents that kind of match your expert information needs, then you can also use that data for evaluation. And you can generate like thousands of these kind of question document pairs. So the second part is that the research scientists or the experts also don't really want to spend time on annotating search results. So we have embraced a paradigm called LLM-as-a-judge, where we actually use powerful language models to also judge the search results. And this has resulted in a method that we implemented in an open source package called Ragilo, of which Arthur is the primary author. And what we see here in this graph is that you can use this approach, maybe not to exactly mimic the judgments of experts, but if you use this kind of LLM as a judge to rank different iterations of your search system, the ordering of the human experts and the LLM as a judge will actually yield the same best system. So there are many, of course, evals framework. What makes Ragilo kind of unique is that it uses this ELO-based scoring system, kind of a tournament style system where pairs of different answers, like chess players in a chess tournament, are evaluated, and then ELO points are added or subtracted. So you see that in more detail here. And basically, it yields at the end of the road, even if you don't have a gold standard or a properly defined benchmark, it yields you an ordering of your system candidates in terms of ELO scores, which is highly likely to correlate with expert judgments. And now, in the second part of this talk, Arthur will talk about how we can make judgments like this actually useful for making these systems better.
Thank you, Jakub. Okay, so let's jump right into it. Let's waste some time. So Jakub mentioned we have all of this complex agentic-based architectures for search and for RAG, etc. And another question is, how much time do we spend optimizing these prompts, right? If we have multiple prompts, what do you do? So let me introduce to you like a simple, not so simple, but simplified deep research architecture, agentic architecture, that it basically have the planner. So a user query comes in, a user question comes in, I have this planner that creates a plan for research, writes queries, and decides when to stop, when you have enough information. Sends these queries to an extractor that reads hundreds, maybe thousands of documents, and extracts information for each query. A merger grabs all of this information and summarizes it into actually useful chunks of text. And the final, a writer that grabs all of that, so all of these summaries and actually writes a full long-form answer. So in a more detailed way, let's say we have a user query that wants a full report about AI accelerators. So the planner first comes in, say, okay, I need to do all of these things. I need to have this plan in my mind that what I need to search. It writes, for the sake of simplicity, only 3 queries that I want to search. And all of these queries go fetch hundreds of documents. Each one of these got fed into a single extractor that goes through a batch of documents, extract, okay, this is actually important, this is not important, this actually matters, this doesn't matter in the end. Feed this to mergers that grab all of this hundreds of information from thousands of documents and write short summaries for each of these questions. So essentially each sub-question, sub-query, sub-task, whatever you want to call it, becomes like one short answer for that, and then the planner comes in and say, oh, okay, this is good, I have new information, but actually missing something about TPUs or whatever, and I read something here that is actually important, and maybe I want you to know more about that. And it goes again and again and again, creating more queries and searching more documents, reading more stuff, until it says, okay, I'm happy now, I have enough information, move on, writer, give me the final PDF, give me the final report. Then create like a long form report for the user. So here we have 4 different agents with 4 different prompts, with multiple different tools that each one of these can call. So the question is, as we scale this up, more and more agents, how many unique agents you may have in a single pipeline? That can grow a lot, right? And how do you optimize this, right? If you don't want to spend time writing each of these prompts, fine-tune each of these LLM calls and the tool descriptions, etc. Well, reinforcement learning is a possibility, like it's an option if you want to go into that route. If you have the budget and the data and you have access to the LLMs and the weights. And actually, it is not that simple, because if you know about how backpropagation and fine-tuning of LLMs works, this is not really differentiable. So we cannot really just go I have this graph of agents, go forward, do a backward propagation and updates the weights. That's not going to work, right? It's not that simple. An alternative is to say, okay, let me optimize these agents itself, like not touch the LLM directly, but let me actually optimize the prompts. And there's actually been a quite popular field recently, in the last few years. There have been a few different papers talking about different ways to do this. So if you have a multi-agent system with multiple different prompts, tools, etc., how do you optimize this? There are a few approaches that came up in the last year and a half. And we decided to say, okay, does this work? We decided to take some time to actually go deep into this and see, can we actually solve this problem? Can we actually make this work in practice? Because this is all like research papers. Does it actually work in a real life scenario? So we picked two of these. First called TextGrad got quite a lot of attention because it got published in Nature. So it kind of break through the bubble of AI and actually go to the more broad science community. It's a paper from Stanford people who got published in Nature in March, but it was initially released middle of last year. The idea is that you have LLMs to grab the outputs of each of your agents, each of your individual steps, and ask an LLM to essentially say, is this good, is this bad, and write me a feedback on that output, and use that to write another feedback for your prompt, and then you're essentially doing a fake back propagation through your graph of agents, right? You're asking an LLM to update your prompts iteratively, and then for each of these prompts, essentially ask another LLM, okay, this is my prompt, this is a feedback that I have received about this, or rewrite this prompt for me, for this agent, for this sub-agent. Another option is the called GPA that was published this year, like a month ago. It's essentially the same idea, but what it does is that it has a really clever way on how you are selecting which agents you're going to optimize, how you handle, because if you run this thing wide, you're going to create thousands of different prompts. So GPA tries to solve this by having really clever methods to select which things actually work, which one doesn't. I'm not going to go into much detail here, but you can read the paper, how they do it, and go deeper into that if you want to. Cool. TLDR, you have a multi-agent system, have outputs, you have a feedback, you ask an LM to get this output and say if it's good, is it bad, and you have another thing to rewrite the prompts for you. So if you run this, you have a new agent, if it's good, you keep going, you have a new agent pool, and have this iteration going on and on and on. And in the end, you can do this through all of your agents in some clever way, and then you have optimized each of your sub-agents for your task in the end. Cool. So we got these two methods and say, okay, does it work? How does it do in real life? So we got this, we run these two things and another one, I'm going to talk about it, through a benchmark called Scholar QACS. So our goal for this was to say, okay, let's do on a thing that people can actually do them by themselves later. So it's like we use only open available data sets and APIs for doing this. Use this Scholar QA benchmark data set. So these are 100 questions from a computer science that actually use LLM-as-a-judge for annotating the final answer. And for searching, for our actual search API, we use this Deep Research Gen search API that searches on the fine web data set, if you are familiar with it. So we have two different agents that we started, a really, really minimal prompt, super simple. So for each of our sub-agents, the prompt is essentially, given a query, write me a report. Given a document, find the relevant information. Give me this information, do this. So basically a really simple one-liner prompt for each of these agents. And another one that was a human-created and optimized prompt that we use internally. So this was a long time development that we took, like a lot of hours and hours of our crafting this and fine-tuning it and improving it over time, over months. And we asked the LLM to say, okay, start from this. We got these methods, the GPA and the TextGrad, say starting from this prompt, run through these methods and see how we get in the end. And we also get, so all of our experiments were running GPT 4.1 mini, just for simplicity. And we also use this OpenAI tool that they have released for automatically optimizing prompts, just to see how that compares to like what is available out there if you just Google optimize a GPT prompt. This is what GPA came out with this optimization. So my laser pointer was not working for whatever reason, but essentially we started from a really simple prompt. At the top is just the simple prompt, and it optimized the planner prompt first and got better. Then it explored all of these possible branches while it was exploring. So basically, you got optimizes one of the sub-agents, run through the data set, see, oh, is it good? Is it bad? If it's good, it adds to a pool, and then go to the next sub-agent, optimize it, and keeps exploring the different possibilities of prompts until you get the final result. That is on the right over there, on the left hand side for me, right hand side for you. That is, if you look at that, it's essentially optimize the planner first. It got better, then it got the I think it's the answer writer, I don't know. Then the information merger, then the extractor. So you keep optimizing a little bit and got to that point, which was the best agent in the end. And this is what TextGrad did. So it was a little bit more drilled down. And if you can see, this is the best one that it got. And it was, so if you think about it, each one of these costs about, each one of these nodes in the graph for running through the whole thing costs about $30 to run through the whole data set. So yeah, that was not very cheap. Sorry, Jakub. And that's the results that we got in the end. So let me just run through what this means. The first bar is the minimal prompt, so the agent with no optimizations whatsoever, the most simple prompt we got. And the red and the darker blue bar is the same prompt after running through the optimizer. The light orange is the one for our human prompt that took months and months to optimize, and the darker orange is, okay, starting from this agent, optimize it and see how far it got. And the silver gray one is the OpenAI optimizer, prompt optimizer that they have available. And the truth is, this one is for TextGrad. The middle one is the GPA using their own meta prompt they have in the paper. And the right one is a meta prompt that was a little bit tweaked for a specific task. Yeah, so the takeaways of that, well, GPA works quite well, better than the TextGrad one. The gains were way more pronounced when starting from the simple prompt, so we actually have more space to explore and got better over time. TextGrad updates and prompts were too short, too simple, really didn't capture a lot of nuance and didn't change much the prompt, so did not improve as much. The best at GPA tried about 41 different optimizations or 41 different prompts. TextGrad took over 60, and it didn't got as good as. And GPA requires way less tries, way less iterations. So it's cheaper. So it runs a little bit better, it's cheaper, faster. It's a more interesting approach overall. So wrapping up, do you want to take over?
So thanks. So basically, we wanted to show you how sort of RAG is a little bit old-fashioned now, and these more complex agentic workflows are taking over the construction of valuable artifacts in enterprise. And what we're seeing is that manual prompting is really kind of limited, and there's a lot of potential in this self-learning approach. If you have some form of eval, then these kind of either genetic or backpropagation imitation approaches to these multi-agent systems can really bring you a lot of improvement. And yeah, so I think the main question here is, how do you properly evaluate these long format responses, like research reports or customer background reports for sales or tender bids for companies. And what we are really seeing is that if you have examples and you have this sort of ELO-style approach, that's a very promising avenue of actually bootstrapping both the evals and the optimizer by just calibrating it on a few expert judgments. And
yeah.
yeah.
I have a question, can I ask?
Yeah.
In this whole architecture, is there a possibility to have a knob which decides the depth of the research? And if yes, how it propagates to all the orchestrator or a supervisor and then other different agents, which says, okay, this is a normal research, this is an intermediately and the next phase is like I need a very deep research.
Yeah.
Is there a possibility, and if yes, how we can inject that?
Yeah, so when we're looking at for the deep research agent, you mean, right? When we're looking at sort of the quality of the deep research agent, there are kind of two heuristics to take into account. One is, are you converging? So are you actually in each new iteration actually retrieving net new documents that are relevant, right? So basically, that if that starts to saturate and you start retrieving the same documents or no relevant documents, you should probably stop. And the other heuristic is just budget. So you can just after some a million tokens or 5 minutes, you usually want to cut it off. But of course, that budget is determined by the value of the task. Does that answer your question? Maybe we should talk more in the break. Yeah.
Yeah, so we talked mostly about optimizing the prompts. And like my problem with building systems like that was that there's a lot of more, like you mentioned the RAG system, you mentioned the extraction mechanism from the document. I don't know if you also have a RAG system for the documents that are picked up, and also optimize on that pieces. And the other part of my question would be, when you see that something is not working, how do you pinpoint which part of this whole architecture you have to readjust? Because it gets kind of complicated.
Yeah.
You can see that you didn't find a relevant document, or you find a relevant document, but the answer is not there. And how did you then start to fix up the system?
Yeah, so this is basically what Jakub was talking about, is that how do you know when to stop, right? If you have an agent, how do you know if it's still getting new things, still getting useful results out of that? So we have basically stopping mechanisms in each of these to say, okay, is it still gathering useful results or not? If not, stop.
But I think the question is more about, can you just optimize the prompt, or can you optimize the whole architecture?
Did you actually try optimizing other parts of the
Yeah, so in this case, yes, it's actually optimizing not creating new tools necessarily, but like optimizing how the LLM see the tool, like the tool a description, the parameters, a description, so it knows better what to expect from that parameters from that tools. So that is actually also getting optimized here. It's because it's part of the prompt, kind of, right? The tool, a description, et cetera, and also there's also a possibility to say, maybe drop this parameter, like I drop this tool, it's not really helping, or don't use this tool that much and more. So over time it gets incorporated into the final prompt optimizer.
How do you manage to pinpoint if you can see that we have this in our corpus of data, but it wasn't picked up? Yes, like we have an issue.
Yeah, that's
recall problem.
Yeah, this is like classical information retrieval problem, right? How do you optimize the recall for your problem, right? For your queries. I would say this is not necessarily a problem with the agent itself, but more maybe a problem with your pipeline of retrieval, the actual OpenSearch index, the queries, or whatever you're doing on the backend to actually retrieve it. So in this case, like we're not touching the index or the search itself. It's just we expose the tool to the agent to search. So it just sends a query with some parameters like how many documents, depth, et cetera, and the backend does the search. Like we're not actually going there. But I'd say if you have a problem there, I don't think optimizing the agent would be the best choice. Like look at your actual retrieval pipeline. Is your pipeline working well for this case? Maybe then you can look at optimizing embeddings, optimizing the index, et cetera, et cetera.
Question, do you need for the deep research agent reasoning model or just simple LLM?
In this case, no, but it could help.
Yeah, so what we're seeing is that if you look at this diagram here, right, so that it's very helpful to have a very strong model for the orchestrator, right? That really matters, because like a weak model will not be good in tool calling, and there's some level of reasoning involved, but it does not have to be an agent that actually outputs the reasoning trace.
And do you have it like in this part?
Yeah, so we're usually using like 4.1 or something like that for the orchestrator, and then maybe 4.1 mini for the individual agents, because they need to be like fast, and there's a lot of tokens being consumed.
For these specific experiments, it's all 4.1 mini, but in production, we actually probably use 4.1 as the main one, and everything is a smaller one.
For LLM as judge, I think some sort of reasoning is needed, right? It's better to have some reasoning which is evaluating the searches.
Depends on what you're choosing.
One of the issues could be, I did a lot of web searches, and it depends. Let's say I'm taking top 5 results which got. There is a possibility that what I'm looking for is not in here. So that part could be improved using some reasoning model like DeepSeek or.
Yeah, it's really about the sort of the raw quality of the model. We have tried, for example, with some smaller open source models like Gemma or Llama, smaller models, and they were just not good enough to do either the LLM-as-a-judge or the orchestration part.
I was facing this issue, and I solved it using GLM 4.5b. It is a model from ZAI.
Yeah.
Like, months ago. And then the quality of the search and the raw information judgment plus a loop to get something good.
Yeah.
That part was there, and it's quite cheap.
You can imagine especially the evaluation to be kind of like you're actually kind of distilling the knowledge of the larger model in some sense, right? So yeah. All right, thanks a lot.